Okay, hi, good morning everyone. So thank you Ben for giving the opportunity to share my research work. So this is Vinu Madhan from India. So I'm going to share my MOF can able to make an applications in the fuel cells and the pollution suppression. Okay, so here we mostly focused on the suppression. The final work should be in the fuel cells. So let's see the what are the MOFs. Okay, so introduction to the metal organic framework. So it is a porous material. There are different kinds of sizes. So it should be starting from micropores to macropores. So macropores should be less than 2 nanometer. If it's a mesopore, 2 to 50 nanometer. If it's a macropore, so it's more than 50 nanometer. So there are some examples. It should be the surface of some chicken eggs.
Oh, hey, Vinu. Hey, I'm sorry. I think your slides aren't transitioning. I'm not sure if. Yeah, I'm not seeing your slides change. Oh, there you go. All right. Yep. Whatever you just did made it happen. All right. Hang on one second. I'll put your voice back on.
Okay, now it's changing. Okay, okay. Yeah, so the introduction to the metallographic framework. So it is the porous material. Okay, so it should be the different three kind of pores. So micropore, mesopore, and macropore. Okay, so there are some examples. If it's a micropore, so it should be the surface of chicken egg cells. If it's a macropore, it should be a monolithic column. If it's a mesoporous, it's something like the carbon membrane. So there are some kind of examples. One should be the activated carbon, zeolites, covalent organic frameworks, then microporous polymers. Here I am going to discuss about the metal organic frameworks. So what is the porous material? There are two kind of porous material. One should be in the nature, another one is the artificial. Okay, so if you are taking the nature porous material, it should be the lungs, then bone, then coral or soil, butterfly wings, then lemons, egg cells, then sea sponge, snow, and sandstones. So these are the some kind of naturally occurring porous material. So when we are saying the artificial porous material, so it is the man-made. So the example should be paper, cloth, chalk, brick, concrete, sponge, bread, cake, ceramics, and some kind of insulations. Yeah, yeah. So when we are saying that activated carbon, so it is the some kind of organic non-ordered structure. Okay, so there are different kind of porous in this material. It should be the macroporous, microporous, and also the mesoporous. When you are taking the silica materials, okay, so the silica and the aluminum based large porous amorphous structure with disordered channel. Okay, so this is the difference between both activated carbon and silica materials. So when you're taking the zeolites, so it should be the inorganic non-ordered structure. So from this we are constructing the metal organic frameworks. So the microporous are part of the crystal structure. So it should be mostly or synthetic, and also the aluminosilicates, and also the cation can be sodium or calcium and ammonium. So these are some kind of zeolites examples. So when you are going to metal organic frameworks, so their huge surface area and also the porous volume makes them potentially useful for the large kind of applications. It should be mostly the storage applications. So these also called as coordination polymers. So before we know about this kind of coordination polymers, so this is the traditional method. So from this traditional method, they created some kind of porous materials. Okay, so there are still a very active research area. So it's growing field right now. Then similar materials without metals are called the COFs. So that is the covalent organic framework. So this is purely organic based. The metal organic framework should be inorganic based. So So these are some kind of examples, GIF or MOF or some kind of MIL, some kind of HKHT. So these like the institute names. So the first MOF started in MIL. Okay, so it's from the Professor Omar Yagi. So why do we want to use this kind of metallographic framework? So it is an why alternative fuels. So it can reduce the dependence on the foreign oil, then harness renewable energy sources, then new opportunities for the agriculture also, then clean air in cities, and also it can reduce the transportation cost and also reduce the greenhouse gas emissions. So what are the alternative fuels we can use? So here we can see the example ethanol from the corn and wood. If you're taking natural gas, so that it should be the 85% of natural gas used in US is domestic. So the natural gas from the domestic gas or oil fields, some kind of deep sea methane hydrate fields. Also the landfills also biomass. So when you're taking biodiesel from soya beans and vegetable oils, then hydrogen. So it's from the natural gas, also the water or electricity and coal. If you're taking the electricity, it's from nuclear and also the hydraulic, electric or solar and wind powered plants. So these are the some kind of alternative fuels. So in my research topic, my research group, we are mostly focused on the aluminum metal because it is highly cheaper material and also it's highly environmentally green material. Okay, so it's not highly poisonous compared to the other metals. So that's why we are focused mostly on aluminum. So we are taking MOF. Okay, so there are different synthetic conditions. Okay, so it should be metal cluster with some kind of organic acids. Okay, so here there are some kind of examples. So the benzene dicarboxylic acid or tricarboxylic acid or some kind of imidazole also. So when it's going to combine with the metal and the organic liquor, so it will form like a porous structure. So there are some kind of examples, MOF or MIL or HKHT or GIF. Okay, so how we can synthesis? So metal salt with ligand, we need to use some kind of solvent. There are so many cooking methods, so it's like a pressure cooker. Okay, so we can use it for 30 minutes to even more than 3 days or 5 days. Okay, so it will cook very slowly. So finally we will get some kind of porous structure. Okay, so that should be some kind of solvothermal microwave, sonar chemical or slow evaporation, mechanochemical, electrochemical. Okay, so these are the some kind of synthetic methods. So mostly here we are using the solvothermal methods compared to the other, because other methods we can use very small time only. So structure of metallographic frameworks at the mesoscopic or macroscopic scale. Okay, so when we are using the synthetic method, it will form like a 0 to 3 dimensional in its structure. So it will start in 0 dimensional or 1 dimensional or 2D or 3D in its structure. So there are large porous apertures in a series of metallographic. So when we are changing the organic linker, so it's from the smaller linker to very longer linker. So what will be happening? It will form like a microporous to mesoporous in its nature. Okay, so it's depend upon the our linker size we are using here. Then development of the Cambridge Structural Database, so CSD, subject to the collection of MOFs in the past and the present future. Okay, so when we are looking the earlier, so it's going to grow each year because of the much more applications in the field. So when you are looking the 2017, so it reaches more than 70,000. So when you are looking now, it's 2021. So maybe it's much more because everywhere the MOF is going because of the applications. So year by year, it's increasing the reports also. So here we can see the aluminum MOF. So when it started from the 2003, Professor Omar Yagi. So he is the first guy developed the porous metallographic frameworks. So that is the MIL 53. So now it's become huge number of MOFs. Okay. Then after that, they consider some kind of zirconium or some kind of zinc or some kind of other transition metal MOFs also. So these molecules are changing the world. So it should be some kind of most applications in methane, cleaner than the petroleum. Then hydrogen, the cleanest fuel. Then carbon dioxide, so the determinant to our planet. Then water, fresh, cleaner, and also the most needed for us. So these are the some kind of MOF. It's starting from the microporous to the mesoporous in its nature. Then some kind of application, hydrogen storage in the nanoporous material. Then methane storage. So these are the some kind of applications. Then we can using as a catalyst. So it is acting as application in the heterogeneous catalysis also. Then so defects also it's playing much more role in the applications. Then post-synthetic modification. So when you do the modification in the surface, so it will act as a much more application. So it will when the normal material is not going to act as application. So when you are going to do the post-synthetic modification, so it will act as a huge applications also. Then separations. Okay, so it can act as a green fuel when we are separating the mixed membranes. So in this content, so we use the 4 applications. So one should be the separation, then catalysis, then post-synthetic modification. Here we are mostly focused on the aluminum MOF. So finally, only one work we use the zirconium and the hafnium MOFs. So the first one we use the 2D aluminum MOF with the Tetrazine-based membrane for the ethanol water separation. So here we use the Tetrazine for the membrane making. Then finally we got the good results compared to the other normal materials. So it is the highly useful material for the greener in fuel. Nowadays in India also we start using the green fuel. So the ethanol is a fuel in the public transport also. Compared to India, other countries are using much more than this kind of fuels. So this is the some kind of price list in the other country, Canada, China, or US or Brazil. Okay, so compared to India, they are using much higher than us. So these are the some kind of preparation. So how the membranes we can prepare. Okay, so it's like a structure intermolecular interaction, then rigid pore size. Okay, so here it's going to make like a hydrophilic or hydrophobic in its nature. So the organic polymers, so the PVA, chitosan or cellulose acetate, so it will form like a hydrophilicity. So the disadvantage should be easily swelling or weak mechanical stability. When we are using inorganic material, zeolite, carbon, moleculars, so can solve the swelling problems, but high mechanical stability also. So the disadvantage should be fragile, form crackers and low reproducibility. So that's why we are introducing the metal organic framework into the organic polymers. So the chitosan should be the hydrophilicity, excellent forming ability, then easy modification, and also the chemical stability. It is the high degree of swelling also. So that's why here we are using the inorganic materials, that is the metal organic frameworks. So mixed matrix membranes. So the combination of organic polymers with the inorganic materials. So finally it will form the highly stable, then uniform micropore structure, then controllable surface functionality, and also the high pore volume. So when we are using the synthetic methods, here we got the defects also. When you are using water, it will form the normal porous in nature. When you are using the ethanol synthesis, so it will form the defects also. Here we use the aluminum with the MBA ligand. So here it will form CuSO7. So we make as a our MOF name CuSO7. So this professor, he is using the GIF material. Okay, yeah, so he got the good results, but when you are comparing with his results, so we got the highest in its nature. So these are the some kind of professors, they are using some kind of water ethanol separation, and they got the really good results. So here we got more than the other materials. So even the mixed matrix membranes, CS-based membranes, even GIF. Okay, so these are the traditionally used materials. So when you are looking the borderline, so we crossed the borderline compared to the other traditional materials. So this is the first time we got the good results from the other traditional materials for the water ethanol separations. Then the same one we used the 3D aluminum MOF. So here also we got the good results for the ethanol water separation. Again comparing with the 2D material. So in the 3D material we got higher than the ability for the 2D materials. Then catalysis. So when you are using the same here, we use the aluminum with a different kind of linkers. Okay, using the microwave method. So it will form the easy within 30 minutes. Okay, then we use it for the catalyst. Okay, sulfoxidation. Then finally, the tetrazine containing zirconium and hafnium of for the post-synthetic modification. So when we after synthesis the tetrazine with the zirconium and hafnium, so we modified with some kind of organic material, that is the click reaction. So our group can be attached. So it's depend upon the inverse electron demand disorder reaction in the chemical biology. So using this method, we used the positive modification for the tetrazine. Because why we use here, that this material can act as a hydrophobicity and also the oleophilicity. Okay, when we are post-synthetic modify, so the MOF material, it will make as a hydrophobicity and oleophilicity. So here we can use the oil water separation. So we already know there are a lot of pollution happening in the sea level. So using this kind of material, we can reduce the pollution also. So you can see here, this is the normal MOF material. So the zirconium and hafnium. So when you are using the post-synthetic modification, that is the C6 or C18. Okay. So here we use the C6. So it will form the hydrophobic in nature. Even after post-synthetic modification, so it's not going to reduce the surface area and the porosity that much. So it should be very less. So that means the MOF should be highly stable in the after post-synthetic modification. So here we use the simple lab material for the oil water separation. So you can see here, it's the hydrophobic MOF sponge, that is the melamine sponge. So it can separate the both oil from when you are dipping here. So it is the required oil. Okay, so it's not going to mingle with the water because it is in the hydrophobic nature. So finally here this is act as a green fuel in the all nature. Okay, so the MOF material can act as a different kind of applications also. Okay, thank you for listening. So if you have any questions, please let me know.
Hey, thank you. That was a great talk. You're doing a lot of really cool stuff with the MOFs. I was not aware of some of that could even be done. So that's really cool. So to the chat, please feel free to get your questions in, and we'll go ahead and go through a couple of them that we already have. So for the ethanol water separation, how's the stability of that membrane? Have you done any sort of like
Uh,
long-term duration studies or anything like that with it yet?
yes, yeah, we measured the long-term duration in, maybe we dipped the membrane in the water and the ethanol.
Mm-hmm.
So after 1 month or 2 months, so we make the stability. So how it look like?
Ah, okay.
So because of the here, yeah, because we are use the aluminum. So when
Mm-hmm.
you are comparing with the other MOFs, so aluminum is much higher stability.
Oh, really?
So that's why
Interesting.
we choose it here. Yeah, yeah, yeah.
Hmm.
So even it will stable up to more than 600 degrees Celsius calcination.
Okay. Okay. So it's
Yeah,
also more stable just sitting in the ethanol water mixture over a long period of time as well.
yeah, 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 yeah.
Interesting. Do you have an idea of why that might be?
Because of the linker binding with the metal.
Ah, okay. Okay. So it's
Uh,
a stronger binding effect.
yeah,
Interesting.
yeah, stronger binding. We cannot break very easily.
Mm-hmm. Mm-hmm. Okay, that's interesting.
Yeah.
Okay, so with the oil water separation that you showed there at the end, do you have an idea of how much oil could be removed per, let's say, milligram or gram of the MOF?
Yeah, we use 5 to 10 milligram. That's it.
Wow. Okay, and
So
how much oil was that actually removed? Wait,
that's we
approximately.
cannot calculate it approximately maybe I don't know how much the grams it should be.
Okay, yeah, that's okay. I was just curious, because as it scales up, it's interesting to see, you said it's 5 to 10 milligrams of MOF. That's a really, a relatively small amount, but and in the
Yeah,
pictures, it looks like
yeah,
it picked up a whole lot of the oil. So that's what I was curious about was what the
yeah. We
ratio
did
looks
not
like.
weigh how much. Yeah, yeah,
Yeah, yeah,
yeah.
yeah. No, that's okay.
Yeah.
I guess along the same lines, is the MOF reusable? Because it looks like the oil comes out of it. So are you able to like, you know, separate the oil, move the oil somewhere else, and then basically clean them off out and use it again?
Yeah, maybe we can use it. I think more than 50 times.
Oh wow. Okay, that's
Yeah.
that's very reusable. That's impressive.
So yeah, up to that it will stable. So more than 50 times.
Oh wow, that's really impressive. Okay.
Yeah. So
Um.
this the last work we are working right now. So still it's not published.
Oh yeah,
Yeah,
yeah.
yeah,
Okay, that's very cool.
yeah.
So you mentioned aluminum in particular as one that you like to work with because because of the cost. Basically, it's something that could be scalable. Um,
Yeah.
is is that something that would be? I don't. I know a little bit about MOFs. So this may be a very simple question. Is
Uh-huh.
that something that's scalable? Like if let's say you find a perfect use for it. Let's say maybe the oil separation or something like that.
Yeah, yes, but here in lab, I think we make one time for more than 1 kilogram,
One
even the large
kilogram.
scale.
Wow.
Yeah, yeah, yeah.
Oh, okay. All right.
Using
That's
the lab method.
yeah.
There is some kind of company also like A520 basolite.
Hmm.
Yeah, yeah. So they are producing tons large scales like some kind of mouse.
Okay. All right. So that's okay. That's very much scalable then. That's really cool. Like I said,
Yeah, yeah. So
I
if
know that
someone need, yeah, we are producing more than 1 kilogram in one time.
that's fantastic. Okay. All right.
Yeah.
So that looks like that might be all the questions we have. I'll give just another second or two if anybody wants to jump in with one. But I'll go
Yeah, yeah,
ahead and
sure.
I'll say thank you again. It was a fantastic
Yeah.
talk. It's really really interesting work that you're doing.
Thank you, Ben, for inviting me.
Yeah, absolutely.
It's
Happy to
a
have you
great
on.
time to meet you. Thank you.
Absolutely. All right. So thank you very much, and we'll be back at about 10:40 for our next talk, everybody. Thank you.